Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as stationary waves. Fine, let's see this. Let's try to find out frequency in parallel position. Parallel or longitudinal position. Right? Now when the prongs are in parallel position, let us see how do we determine the frequency. Right? In this this is your pulley. When the prongs are pulled outwards, there would be a slack in the wire or there will be a slack in the string. Right? So the string will move in one direction. When the prongs come back to its original position, there will be tension on the string again, requisite tension on the string again. When the prongs move outwards again, again there will be slack in the string, but now it will be on the other side. So if the prongs move out again, the slack will be on the other side. So this is how, as the prongs move out, come back to its mean position and move out again, you would have only half a wave completed. Right? Now this is how it will work in parallel position. So I can say in this position, the fork is placed in such a way that the motion of the prongs is parallel to the length of the string. Right? In this case, I can say that the frequency of the fork is double the frequency of fork is double the frequency of the vibrations on the string. Is double the frequency of the vibrations on the string. Fine. Now let's try to explain why. I can say that initially when the prongs move outwards, the string becomes slack. And moves in a position. As shown in figure 1. Right, this is my figure 1, figure 2 and figure 3. Okay. Now, as shown in figure 1, right? Now, when the prongs move, as the prongs move inward, the string becomes tight again. As the prongs move inwards, the string becomes tight again. The string becomes tight again. Right? Now, when the prongs move outwards once again, when the prongs move outwards once again, when the prongs move outwards once again, the string becomes slack. The string becomes slack, right? Becomes slack, but this time the string has acquired vertical velocity. But this time the string has acquired vertical velocity. The string has acquired vertical velocity and while on account of inertia, the string now moves in upward direction. On account of inertia, the string now moves in upward direction. Right? So, by the time the fork completes one vibration, by the time the fork completes one vibration, only half the while the string would have completed only half the vibration. The string would have completed only half the vibration. Right? So from this we can safely say that the frequency of the tuning fork is double the frequency of the vibrating string. Therefore, I can say that the frequency of tuning fork is double the frequency of vibrating string. Fine, do we get this in clear? Now, once we have this, let us assume that n be the frequency of the tuning fork. Let n be frequency of tuning fork. If n is the frequency of the tuning fork, then I can say that, let's assume n is the frequency of the tuning fork, then I can say that n is equal to 2n, but the value of small n in Medley's experiment is nothing but p, we've done this derivation, p upon 2l square root of t by m, right? Therefore, I can say that 2 and 2 gets cancelled. Therefore, the frequency of the tuning fork is p upon l, 2 and 2 gets cancelled, square root of t upon m, right? Now, I can say that squaring both the sides, if I square both sides, I'll get n square. I'll get n square is p square upon l square into t upon m, right? So therefore I can say that n square l square m square is equal to n square l square m is t TP square, right? Now for a given tuning fork, the frequency of the tuning fork and the length of the string is constant, but for a given tuning fork, N is constant. I can say also N and M are constants. Therefore, I can say you can say that TP square is constant. So in parallel position you get TP square is constant. Fine, do we get this here? Next, let's move on to perpendicular position now. Perpendicular or transverse position. Right? Here the string would move this way and this way, as the prongs would move inwards and outwards. Right? Now, I can say that in this position, the fork is so placed, that the motion of the prongs is perpendicular to the length of the string. The motion of the prongs is perpendicular to the length of the string. So thus, when the tuning fork completes one vibration, the string also completes one vibration. When the tuning fork completes one vibration, the string also completes one vibration. Fine, do we get this in clear? Therefore, I can say that in perpendicular position, the frequency of the fork is equal to the frequency of the string. Therefore, in perpendicular position, the frequency of the fork is equal to the frequency of the string. Right? In that case, I can say N is equal to N. But for Medley's experiment, N is equal to nothing but T upon 2L square root of T by M. Right? In which case, I can say that squaring both sides, I'll get N square is P upon 4L square T by M. Right? So in which case you will get TP square is equal to 4 N square L square M. Right? But for a given tuning fork, N is constant. Also the length and mass per unit length are constant. Therefore, I can say that TP square is constant. So whether it is parallel or perpendicular position, TP square is going to be constant. Fine, do we get this thing clear? Now, Let us assume, let's find out the relation between parallel and perpendicular position. Relation between parallel and perpendicular position. Right? Now let us assume that initially the tuning fork is placed in parallel position. Let the tuning fork be placed in parallel position. Right? Now if the tuning fork is placed in parallel position, let us assume that T is the tension on the string, L is the vibrating length, T is the tension on the string, L is the vibrating length, and let us assume that the vibrating length is so adjusted so that I get P1 number of well-defined loops on the string. Number of well-defined loops on the string. Right? Now in that case, I can say that the frequency of N is the frequency of the fork, in which case I can say N will be nothing but P1 upon L square root of T by M. We've already derived this. Now keeping T and L as same, keeping T and L as same, let us assume that we change the position. The parallel position of the fork is changed to perpendicular position. The parallel position of the fork is changed to perpendicular position. Let's assume that this parallel position is changed to perpendicular position. As a result, let us assume that P2 is the number of well-defined loops obtained in perpendicular position. Number of well-defined loops on the string. In which case, I can say that N is equal to P2. N is equal to P2 upon 2L square root of T by M. Right? Now, both are N, so I can equate the two equations. If I equate the two equations, I will get P upon L, P1 upon L square root of T by M is equal to P2 upon 2L square root of T by M, square root of T by M gone. So in that case L and L is gone, so you will get P1 is P2 upon 2. That's your relationship between parallel and perpendicular position. Fine, do we get this thing here? Now, let us study the vibrations in an air column. Let's try to find out vibrations in an air column. Right? Suppose if I had an air column, which was, say, hypothetically assumed fixed from one end. So in that case, you would have the air wave moving this way in it, right? Let's see what happens to the air wave inside a vibrating, inside an air column. Now, when air column is enclosed in a tube, this is your tube in which the air column has been enclosed. When air column is enclosed in a tube. Now when the air column is enclosed in a tube and is disturbed by a source of sound, when the air column enclosed in a tube, say, is disturbed a source of sound. You already have some air inside, right? Now, due to sound, there's going to be some disturbance in the air column which is there inside the. There's going to be some disturbance in that air that is going to be in that air column or in the tube, right? So as a result of which the air column is set into forced vibration. When air column enclosed in a tube is disturbed by source of sound, I can say that the air column is set into forced vibrations. The air column is set into forced vibration. So there's already air moving inside. When I blow inside it or when I speak inside it, there's going to be some other force that is going to be exerted on it, a periodic force that is going to be exerted on it, and as a result of which there are going to be forced vibrations inside an air column. Now, I can say that the longitudinal waves emitted, the longitudinal waves emitted, the longitudinal waves emitted by the source travel through the air. By the source travel through air, right? And they get reflected from the lower end of the tube, and they get reflected from the lower end of the tube. The air column will hit and will come back, right? Thus, I have two progressive waves that are set up inside the air column, one which is moving down, one which is coming up. The two waves are equal in magnitude and opposite in direction, as a result of which they will interfere with each other and stationary waves are set up inside the air column. That is the reason why you have stationary waves set up in an air column. Fine, do we get this thing clear? So, sorry, I can say thus two trains of progressive wave, thus two trains of progressive waves, traveling up and down, are formed. One, what you are blowing inside the tube, and then it is going to hit the bottom and it is going to move up. So that's the other wave that is coming up, right? So thus you have two trains of progressive waves traveling up and down, and they interfere to produce longitudinal stationary waves. So thus longitudinal stationary waves are set up in the tube. Thus an air column is capable of setting up stationary waves. Now the air column possesses some natural frequencies of vibration depending upon its length. The air column possesses some natural frequencies of vibration. Natural frequencies of vibrations. As the air column possesses some natural frequencies of vibrations depending on its length, right? Now when a source of sound of a frequency equal to the natural frequency is mixed with air, there's some natural frequency, air is already vibrating with some frequency in the air column. Now you are also going to, from an external source, you are going to put air which is equal to the frequency at which it is vibrating inside the air column. Then the forced vibration will be equal to the free vibration, which will give rise to resonance, and as a result of which, because of resonance, a large sound would be produced, right? So I can therefore say that frequencies of vibration, I can say when the source of sound equal to the frequency, when a source of sound equal to, when the source of sound of a frequency equal to, source of sound of a frequency equal to the natural frequency of the air, natural frequency of the air column, so when the source of sound of frequency equal to the natural frequency of the air column is sent, you would have the air column is thrown into resonance. The air column is thrown into resonance, right? And as it is thrown into resonance, it vibrates with maximum amplitude and emits a loud sound. Thrown into resonance, hence it vibrates with maximum amplitude it vibrates with maximum amplitude and emits loud sound. Fine, do we get this in here? So in this case, the node and antinodes of the stationary waves occupy fixed position inside the tube. I can say that the nodes and antinodes, occupy fixed position in the stationary wave. Right? So thus now we know that an air column sets up an air column. Inside an air column you would have stationary waves, right? Now let us try to see what will be the frequency of such stationary waves. Let us find out if the tube is closed at one end. Let's see what is the frequency that is going to be set up. Right? Let's assume that I have a tube. What are the different modes in which I can have? This is the tube which is closed at one end. I would have two trains. Frequency would go, hit and come back. Let's assume that the entire length of the tube is L. The wave goes, hits and comes back. That means this is just one fourth of the wave that is produced, right? So that means this is nothing but lambda by 4. The length of the tube is nothing but lambda by 4. Let us assume that this point is N and this point is A. So I can say that the waves which are sent in an air column in a tube closed at one end are reflected from the closed end. The incident and the reflected rays interfere with each other and produce stationary waves, of which I have already explained to you, right? At the closed end, the air particles are in contact with the fixed wall and cannot move freely, right? Hence, the node is going to be formed at the fixed end. because after this point the air particles are not going to be able to move freely. Since after this point the air particles, when they come in contact with the fixed end, those air particles will not be able to move freely. Hence a node is formed at the closed end, right? Now at the open end the air particles are allowed to move freely inward and outward, and hence there is maximum possible freedom at the open end. Hence an antinode is formed at the open end. So in a tube, in a closed tube, the node will always be formed at the closed end and an antinode will be formed at an open end. Fine, do we get this thing here? So I can say that, yeah, someone wants to ask me something?
How is the wave moving there?
It will go, hit and come back. At this point there is no place for movement of the wave. The sound waves which have travelled inside, they have to be stationary at that point, have to hit and come back. There is no freedom allowed for the movement of air particles at this point. Right? I can say that the waves sent along the air column in a tube closed at one end are reflected at the closed end. Right? The incident and the reflected rays interfere to produce stationary waves. I can say at the closed end, the air particles are in contact. The air particles, you wanted to know why? I'll just write this down. Particles are in contact. The air particles are in contact with the fixed wall. The air particles are in contact with the fixed wall and they cannot move freely. Right? And hence a node, since what is node? Node is a point where the air particles do not move. At this point, at this end, the air particles will not be allowed to move. When the air particles are not allowed to move, that will give rise to a node. That's the reason why you have a node formed at the fixed end. Right? Hence a node is formed at the closed end. Hence a node is formed at the closed end. Right? Now at the open end, air is free to move inward and outward. Free to move inward and outward with maximum possible freedom. Air is allowed to move inward and outward with maximum possible freedom, right? Hence an antinode is formed at the open end. Hence an antinode is formed at the open end. Right? So in the air column, in a pipe closed at one end can vibrate in different modes depending upon what are the conditions. Now the different modes in which it can vibrate, one of the simplest mode I've shown you in this diagram. This is called as the fundamental node, in which you have one node N produced here and one antinode that is produced here. Right? I can say that the simplest mode the simplest mode of vibration is the fundamental mode in which antinode is formed at the open end and node is formed at the close end. In which antinode is formed at the open end and node is formed at the close end. Right, that's the simplest mode of vibration. Fine, do we get this thing clear? Now let's assume if lambda is the wavelength of the wave and L is the length of the tube. Lambda is wavelength and let us assume that L is the length of the tube. In which case I can therefore say that L, from the figure it's very clear, is equal to lambda by 4, right? That is, it is the distance between adjacent antinode and node, right? Hence I could say that lambda is equal to 4L, right? Now let's assume that V is the velocity of waves. V is the velocity of waves. Now I can say that frequency is nothing but V upon lambda. We just found out lambda to be 4L, so frequency will be nothing but V upon 4L. Fine, do we get this thing clear? This is called as the fundamental frequency or the first harmonic. This is fundamental frequency or the first harmonic. Right? So this is going to be my fundamental frequency of the first harmonic. It is the lowest frequency with which the air column tube closed at one end can resonate. It is the lowest frequency with which the air column closed at one end can resonate. So that was one of the modes of vibration. Let's see if we can produce vibration in some other mode also. Let's draw a tube again. Right? I could have this could be another mode of vibration where you have an antinode here, you have a node here, you again have an antinode here, and you have a node here, right? L is the length. Now, in this case, you have how many 1/4 waves produced? You have 3 1/4 waves produced, 1, 2, and 3. These are the 3 1/4 stationary waves that are produced. So therefore the entire length is divided into 3 lambda by 4. Right, do we get this thing here? Let's call this as lambda 1. Right? Let's consider if the vibration mode of vibration, let's consider a mode of vibration in which the tube, let's consider a mode of vibration in which the tube is divided into three equal parts. The tube is divided into three equal parts, right? Three equal parts with two nodes and two antinodes. Nodes and two antinodes. Let's consider this method, which are alternatively produced. Let's assume that let n1 and lambda 1 be the frequency and wavelength. Be the frequency and wavelength. Right? So if n1 and lambda 1 are the frequency and wavelength, then I can say that the entire length of the tube is divided into 3 lambda 1 by 4. You have 3, we already said it is divided into 3 parts. Therefore, I can say that lambda 1 is 4L by 3. Right? Once I know the value of lambda 1, I can say but frequency is nothing but V upon lambda 1. So therefore I can say that frequency is V upon lambda 1, that is 4L by 3. 4L by 3. So that will be my frequency. Now, but this can be written as N1 will be 3 into V by 4L. But what is V by 4L? V by 4L is nothing but the fundamental frequency. Therefore, the frequency will be 3 times the fundamental frequency. In this particular mode of vibration, if you divided the tube into 3 equal parts, then the frequency will be 3 times the fundamental frequency. Right? Let's try to see one more mode of vibration. Let's consider another mode. Let's consider the tube is closed at one end, and let's divide the tube into 4 parts. Antinode, node, antinode, node, antinode, node, right? Let's consider this particular mode of vibration where you have an antinode, node, antinode, node, antinode and node, right? In this case, how many 1/4 waves are formed? 1, 2, 3, 4 and 5. So that means the entire length is 5 lambda by 4. We'll call this lambda as lambda 2. The entire length of the tube is going to be divided into 5 lambda by 4, right? Fine, do you get this thing clear? Now, let's consider a mode of vibration in which let's consider a mode of vibration in which three nodes and 3 antinodes, 3 nodes and 3 antinodes are produced. Right, you have 3 nodes and 3 antinodes equally spaced in the tube. Spaced in the tube. Right? So in that case, let's assume that the corresponding frequency, N2 here will be nothing but 5 times the fundamental frequency, right? In this case, this is the second monotone or the fifth harmonic. Fine, do we get this in here? So thus you can have different modes and for which you would have different types of harmonic. The only thing is that thus only fundamental frequency and the odd harmonics are produced when the tube is closed at one end. For example, guys, if I were to check the previous one out, where I had N1 is equal to 3N, guys, can we see this? When we have N1 is equal to 3N, so I can say that N1, that means this is the first overtone, or the third harmonic, right? First overtone produces third harmonic, second overtone produces fifth harmonic. That means here I have only odd harmonics which are produced in a tube which is closed at one end. The even harmonics are missing, right? So I can say thus only fundamental frequency and its odd harmonics, fundamental frequency and its odd harmonics are produced by the tube, right? Closed at one end. Right? As a result of which I can say that the even harmonics are missing and the sound emitted from the tube, the even harmonics are missing. The even harmonics are missing in the sound emitted from the tube closed at one end. Right? So you would have the frequencies that would be present would be N, 3N, 5N, so on. So thus the frequencies present are N, 3N, 5N and so on. Right? Now I can say that in general, therefore I can say that in general the formula for a closed tube, frequency of the kth overtone, is given by the formula n 2k plus 1, where k could be any number from 1 to infinity. Right? That is the general formula for a tube closed at one end. Fine, do we get this thing here? Right, we'll stop this here for the day. Thank you very much.